So we'll start the second talk of the morning session. Monidipa is a. This is not your first talk, isn't it? So I don't have to introduce you. So Monidipa is going to talk on point group symmetries, and most of you might realize that point groups are very important in crystallography. When you start off crystallography, it is point groups, but even in single particle cryo-EM, wherever you see symmetries, these are very important features that you have to identify right from the beginning. And she will talk about what are point groups and how do you identify those features in the EM images as well. Manideep. Thanks.
Hello? Okay. All right. So what I'm going to talk about, I think, is more or less familiar to the audience since there are a lot of crystallographers here. So I'll just give a general introduction to point group symmetries, and then we will go on to types of point group symmetries that one expects in biological macromolecules, which is what we're interested in terms of EM. So some basic definitions, symmetry element is a point, a line, or a plane about which a symmetry operation is performed. Symmetry operation now, a real or imagined movement of a body about one of these elements, so that after movement, every point on the object is regenerated at an equivalent distance. Proper rotation, where no change of handedness occurs. Improper rotation, there is a change of handedness. So this definitions may be completely familiar to most of you. The elements of symmetry, this point, line, plane, translation, or for complex symmetry operations, combination of the above. So using these elements of symmetry, what are the operations that we can do? So there is identity operation, which means you're doing more or less nothing. Rotation axis, so you rotate something, an object, by 360 degrees divided by n. N is the symmetry axis, Cn is the symmetry axis that one is being used. Mirror plane reflection, inversion center, through that you're doing an inversion of your object. And then improper rotation axis, where you rotate by 360 degrees divided by n, and then you reflect the object perpendicular to axis. So these are the corresponding symbols for each symmetry operation. So just to expand it a little bit, all molecules have the identity operation. And when you're talking about rotation, let's say C1 is a rotation where you're basically not doing anything, so you're just doing an identity operation. Then depending on the n number, 2 or 3 or 4, you are doing rotations of your object by, let's say, 180 degrees or 120 degrees, etc. Mirror plane, so in case of a proper rotation, you can have another axis which is perpendicular to the central Cn as well, and we'll see it in some of the point group symmetries. Mirror plane parallel to Cn is a vertical mirror plane, parallel to Cn and bisecting the second rotational axis dihedral, and then perpendicular to Cn is a horizontal mirror plane. Inversion center, you move all atoms through the inversion center to an equal distance on the opposite side. So in the inversion center may or may not be the atomic center. And the improper rotation axis, as we discussed, is a combination of rotation and reflection. And some of these symmetry operations may be equivalent operations. So we'll come to that as well. So when we talk about rotation in a plane, more or less, so this is an example with a Tim barrel protein. So for a two-fold rotation, you rotate about center, and you regenerate the same object. Now, if you just take this combination, so you have your molecule, and then you have it rotated by 180 degrees, and you just translate it, then in 2 dimensions, then you start getting what is called a P2 plane group, and in addition, you start also generating newer symmetry axes. Again, P3 plane group, so you've taken again the Tim barrel protein and you've rotated it through 2 successive rotations. And again, if you just take this unit and you translate it, you end up with a P3 plane group. Similarly, sorry, there's a mistake. This is a P4 plane group. So again, you take an object and you're rotating it by multiples of 90 degrees, so your n is equal to 4. And again, you're translating it, so you're ending up with a P4 plane group. Now, if you do this, these Cn rotations in 3D, so you're doing this about an axis or a line. So you are regenerating your object. So let's say your rotation is around the z-axis. So the x, y, z molecule will be regenerated as in the minus x minus y z spot. Similarly, you can see here equivalent positions for a 4-fold proper rotation, considering that this z remains constant. You can start getting different, as you are rotating your object, different regenerations of your at equivalent positions. So just to show you, these are the stereograms of the proper rotation axes, and the 2-fold, 3-fold, 4-fold, and 6-fold. And you, those of you who are crystallographers know that according to crystallographic restriction theorem, in lattice, these are the types of rotations that you can have. But when we're talking about biological macromolecules and the internal symmetry of biological macromolecules, then obviously you can have more rotations than this. So again, to show you a combination of rotation and translation, so you're starting off with a 2-fold rotated object, and then you are translating it. So you're creating a lattice, and then as a result of this translation, you are creating new axes of symmetry. And the combination of rotation and translation, when you are rotating an object and then you are translating it along an axis, again, the crystallographers would know that you're generating something called a screw axis. So this would probably become easier from here. So you've rotated, in this case, again, the Tim barrel protein by 180 degrees, and then you have translated it along half the unit cell. So you're generating a screw axis there, which is represented by this sign. And again, you can figure out what are the coordinates of the equivalent position. So if you have x, y, and z, then by doing a roto translation or generating a screw axis, you can end up with, if you're doing this along the z-axis, and then you are translating your molecule also along the z-axis, so you have minus x minus y and z plus half. Is your new molecule position. So another example of rotation and translation where the n of Cn, the axis is 120 degrees, so n is 3. So again, you have rotated the molecule by 120 degrees, and then you have transferred it or translated it along the z-axis by 1/3 of the unit cell. So you're generating this sort of helical structure by doing the roto translation. Mirror, again, reflection along a plane, as you can see in this some image, an image from nature. And again, you can, depending on which axis your mirror plane is perpendicular to, you have different equivalent positions generated for your particle. Inversion, inversion through a point to generate an equivalent molecule. So again, if you look at equivalent coordinates for your molecule that you're working with, so x, y, z would translate it to minus x, minus y, and minus z. And as I mentioned before, that some of these symmetry operations can be equivalent to each other. So just if we take an inversion. On the other hand, if we take a 2-fold, and we say that this is 2-fold parallel to the y, then a 2-fold operation would generate equivalent molecule at minus x, y, and minus z. And now if we have a mirror plane, which is perpendicular to y, again, you end up with a minus x minus y minus z position. So which means that if you do a 2-fold operation, combine it with a mirror, this is the same as an inversion. So these are improper axes in the sense that you are doing a rotation followed by reflection. So just to show you the equivalent positions in case of generating a threefold improper axis. So first rotation followed by inversion. So you generate the symmetry-related molecule. Similarly, again, rotation followed by inversion. So you're generating another symmetry-related molecule. So like that, you fill up the space gradually. So these are the stereograms of 5 improper rotation axes. And again, this is a combination of mirror as well as rotation. So what do we mean? So when we apply all of these symmetry elements, we get something like called a point group. So what is a point group? It is a collection of symmetry elements. If, say, we're talking about a molecule, all the symmetry elements might intersect at a point. So they do not alter the molecule itself. And this summarizes all the symmetry operations in a group. So this is the definition of a point group. And for chiral molecules, in order to be chiral, molecule must lack anything which will cause a change in the chirality, lack any symmetry operations which will cause any change in chirality. So obviously you're familiar with right-handed and left-handed helices, and if you have an original copy, you have a mirrored copy, you change the handedness of the helices. So you can't really do that when you are talking about a point group operation. So the point groups of biological macromolecules are the following. According to Klein's theorem, which was provided in 1884, the only finite 3D symmetry groups are cyclic, dihedral, tetrahedral, octahedral, and icosahedron. So these are the ones that we are going to be focusing. So the cyclic point groups for biological macromolecules, so these are all represented by C and a number. The number is your rotational axis. And C1, again, is what that means is an identity operation, meaning that you are not really doing anything to it. It's it's completely asymmetric. And then you have, as you increase the value of n there, you are getting molecules which have some symmetry. Dihedral, they have 2 symmetry axes, and then there's the high symmetry groups, the tetrahedral, octahedral, and icosahedral, that will gradually come to. So when we talk about cyclic point groups, the first one, the simplest case, is C1. This is an asymmetric molecule, could be an oligomer, and every projection is unique. So when you are taking the projections in an electron microscope, you do not get a projection reappear at a different combination of Euler angles. So what this necessarily means is that for doing a reconstruction, you generally require a lot more data because every projection is unique. So you're not getting the same projection back at different orientations. And there is mirror symmetry between projection at one Euler angle and its opposite Euler angle. So you would be able to locate the symmetry. And the asymmetric triangle takes up the whole unit sphere. So what I was saying is that you would require a lot more data. So you have seen a lot of information on ribosomes. So this is just something I got from EMDB. This is the 50S ribosome bound to ligand, OBGE, and there is no symmetry at all from any of the angles. So if you're working with a C1 particle, you are just stuck with having to generate a lot of data so that you can eventually get a decent reconstruction. C2 has, C2 molecules have one two-fold rotational axis of symmetry. So every normal projection will appear twice, and projections which are perpendicular to the two-fold axes will demonstrate mirror symmetry. The asymmetric triangle constitutes half of the unit sphere, so this is a little bit of an advantage over C1 molecules, meaning that you can actually get away with less data for reconstructions. So this is an example of a C2 molecule. This is a recombination activating gene, or RAG, and this has a C2. And if you just look at some of the projections from different orientations of the molecule, you can start seeing that there would be a twofold in some of these projections. So we just go like this. So C1, C2, C3. So again, the notations that I'm showing are Schwann-Flies notations. These are not the Hermann-Magen symbols, which are more familiar in the crystallography field. So this again is a HIV enveloped glycoprotein. So I just took it for the sake of the symmetry. And you can see that this is has a threefold passing through here. And if you again look at the projections, you would be able to pick out the threefold in at least one of these projections here. So this is how it more or less goes for all CN molecules, which are all other cyclic point groups. And typically, when you say that there is a CN structure, it means that you would have to have at least n identical units. So Cn denotes that at least n identical units would be present in your oligomer that you're working with. And typically, these are organized in circular arrangement in head-to-tail fashion. And the rotational axis is perpendicular to the plane of arrangement of the molecules. Typically, in cases of even symmetry, the projections have mirror symmetry. And in cases of odd symmetry, the projections do not have mirror symmetry. So these are also things which can be figured out, some details which can be figured out from the 2D projections of the molecule that you're imaging, that what would be the correct Cn value of your protein of interest if it does have Cn. An example of a C4 molecule is latrotoxin, and again in the top view you are able to see the way that the molecule is arranged. If you took a projection of that, you would be able to identify the C4. Again, in this orientation, it may be a little bit difficult. So I'll just show you one image from a very long ago. So this was work done by Crowther in 1971, when he was trying to figure out the rotational symmetry of the base plate of T4 bacteriophages. So from the projections, it may be possible to say that the symmetry here is probably C6. He also, what was done was from the rotational power spectrum of the images, it is possible to see that the peaks are there at, let's say, at every 6-fold. So you have a peak at 6, at 12, at 18. So it is possible to take a rotational power spectrum and from there to, thank you. And from there to figure out what would be the correct symmetry of the macromolecule. So not going through all of the rotational symmetry, all of the CN symmetry point groups. Here's a C9, which is a ribonucleoprotein from influenza virus, and this is the way it's organized, and you can see that there is a C9 symmetry. C11 and 12. So I'm presenting these together. This was an interesting story. This is bacteriophage P22 portal and tail machine. So during the preparation of these portals, which were associated with which are typically associated with the tail. So in phages, if you know, there is a right. Right. So what was seen there in the preparation, there was a mixture of 12-fold and 11-fold molecules. So they had to be eventually, so this was, you've been hearing a lot about heterogeneity. So this was a significant heterogeneity in the sample, in the sense that the particles that were prepared, did not actually have the same CN group, so they were different. They did not have the same point group, so they had to be sorted out, and two structures were solved from the same preparation, one with 11-fold and another with 12-fold rotational symmetry. So the next relatively complicated point group now. So these are the simplest point groups from C1 identity. So you have a 2-fold rotation, 3-fold rotation in your biological macromolecule, 4-fold, 5-fold, et cetera, 9-fold, 11-fold, 12-fold, etc. Now, dihedral point groups are slightly more complicated than cyclic point groups. And these structures basically have a n-fold rotational axis and a 2-fold axis, which is perpendicular to it. So you can think of this as two cyclic point groups, which are stacked either top to top or bottom to bottom. So again, the definition sort of indicates that if you have a D1 molecule, it will be a C2 molecule, right? So the first point group, more or less, in the dihedral molecules is D2, which has 3 2-fold axes, which are all perpendicular to each other. And the minimum number of subunits required to make these molecules is 4. Again, here you have some symmetry-related advantage if you have a D2 molecule, because one projection is equivalent to 4 different projections. And projections along 2 folds have a double mirror symmetry. So the asymmetric triangle covers 1/4 of the unit sphere. So one example of a D2 structure is this limulus polyphemous hemocyanin. So we will see a lot of hemocyanin structures here because they have different types of symmetry. There's D2, there's D3, etc. So in this case, you can see the rotational axes perhaps a little bit, or the symmetry in the molecule if I rotate it a little bit. So there is 3 2-fold axis of symmetry in this particular molecule, which makes it easier in the sense that the number of projections required to solve a 3D structure is should be proportionately less, but that also depends on the quality of image and the size of the molecule, etc. Now, if you look at the projections along the 3 axes, so here again, you would be able to identify, looking at these projections and the images corresponding to these basically views of the molecules, that there are the 2 folds that are present in different orientations of the molecule. And if I just correspond that with some of these images, and perhaps it is more clear in these averaged images. So what you can see perhaps is that this projection at this orientation actually correlates with this class average. And then again, if we go to this particular projection at this orientation, it correlates, let's see, probably with this one. And again, this particular projection of the orientation of the molecule again corresponds to specific class averages. I think that may be this one. So, so again, it depends. In order to identify what is the point group of your molecule, it is necessary to have something which does not have images, which do not have too much noise. And the class averages, from the class averages, it is possible to understand what is the type of symmetry that is there. The next higher group is D3. So here, to generate this type of oligomeric molecule, you require a minimum of 6 equivalent monomers. And there is 1 3-fold rotational axis and 3 2-fold axes, which are perpendicular to the initial axis. And the projections along 3-fold axis exhibit 3 mirror planes. An asymmetric triangle covers 1/6 of the unit sphere. So you can see that we are getting to more and higher symmetry groups. So again, another hemocyanin, which is an example. So this is Palinurus elephas hemocyanin, and these are 3 different orientations of the molecule. Now, again in the different class averages of this molecule, you can see that there is one preferred orientation, probably towards the end views were preferred, and during reconstruction, some of the end views were left out. So of the class averages that were put towards 3D model generation, some of the end views were left out or minimized in order to prevent their influence too much on the final structure. So again, looking at the projections, you can see that you can identify the symmetry axes. D4, which requires 4 equivalent monomers, and there is 1 4-fold axis and 2 2-fold axes. Projections along the axes show perpendicular mirror planes. An asymmetric triangle covers 1/8 of the unit sphere. So one example here is Rubisco. This is the Rubisco large subunit octamer. And again, from the corresponding orientations of the particle and the projections, you can identify what are the symmetry elements. D5, by definition, this again requires 10 equivalent subunits. Each projection corresponds to 10 different combinations of Euler angles, and projections along the 5-fold contain 5 mirror planes. Again, the asymmetric triangle covers 1/10 of the total unit sphere. One example of a D5 molecule is the keyhole limpet hemocyanin. So all of these hemocyanins have different types of symmetry. And again, you can look at different projections and try to identify the symmetry elements. D6, there should be a total of 12 equivalent subunits. One example is worm hemoglobin. And just to show you what would be the different orientations and the corresponding projections, so that the symmetry elements here can be identified. Now, D7 is an example that you have been seeing quite frequently over the last few days. So this is Groyel, and this is a slide that I borrowed from Dr. Natesh. So you can see here that you can identify in some of these Egan images that you can actually see the 7-fold axis of symmetry right there. So you would be able to tell that this is a D7 object. Now, obviously, how do we distinguish between a D7 and a C7? So the D7 is let's say the way you think about it, is 2 C7 objects which are stacked on top of each other. And C7 would just be one single layer, right? There won't be 2 layers. But in certain projections, for example, if you're looking at the end views, you may be able to see just the 7-fold cyclic rotation axis. So then you have to look at it in other projections to ensure that in the side views at least, so the top views or the end views will show the 7-fold, and then the side views, through the side views you should be able to detect the 2-fold. So both of these would indicate that this is a D7 and not a C7, because the end view would basically have a 7-fold. Okay, so there are mostly sometimes confusion about the end views of cyclic point groups and some of the dihedral point groups, and how to distinguish them, and how to figure out whether something, let's say, is a D7 molecule or a C7 molecule. And those can be handled via looking at the symmetry of the projections at different views of the molecule. Of course, if the molecule has a preferred orientation, or if there's a lot of noise in the image, then this becomes difficult to do. So now we are left with the group which are called the Platonic solids. So these all have cubic symmetry, and the examples are tetrahedron, octahedron, dodecahedron, icosahedron. And they all follow the Euler formula, meaning the number of vertices, faces, and edges are related by a specific mathematical formula. So again, to show you some of these Platonic solids and the way they're organized. Tetrahedron, there should be 4 3-fold axes and 6 2-fold axes. So this is an example with heat shock protein, HSP26. And again, if you look at these the projections of different orientations, what you see in the dotted line here is a view close to the 3-fold, and then in a solid circle here is a view close to the 2-fold. So from the projections of the different orientations of the molecule, it should be possible to figure out what kind of symmetry is there. The example of one octahedral molecule is the HPV, small surface antigen particles. And again, these are supposed to have 6 4-folds, 8 3-folds, 12 2-folds. And the corresponding projections, some of the corresponding projections of different orientations of the particles are there. And so the final point group, which we'll discuss in some detail, are icosahedrons. This is called the queen of point groups, the reason being that you have a lot of symmetry. And one of the reasons why cryo-EM's 3D structure determination techniques were initially optimized on icosahedrons, or rather icosahedral viruses, was because of this enormous amount of symmetry that is present in these particles, right? So, the notation of the point group is I, and this is a 5-3-2 point group, meaning that there would be 12 5-fold symmetry axes, and there will be 20 3-fold symmetry axes, and then there will be 30 2-fold symmetry axes. And the way that these symmetry axes are organized is that the 5-fold, it passes through the vertices of the icosahedron, and the 3-fold is in the middle of a icosahedral face, and the 2-fold is in the middle of an edge of an icosahedron. So total 12 5-folds, 20 3-folds, and 30 2-folds. So how to make an icosahedron is a very interesting exercise. How do you bring all of these faces, triangular faces, together in order to generate an icosahedron? So you can do some of these exercises if you go to a website called ViperDB. So there you will have an icosahedron generator, and you can play with different size of faces to generate an icosahedral structure. But just to tell you in a very basic fashion what generates an icosahedron. So if you have, for example, a tile of hexagons, and you figure out an origin, right? And then you have 2 vectors. So this is almost like a lattice. So there is this in the h direction and in the k direction. And the angle between h and k is, in this case, 60 degrees, right? So you have specific distances going from the origin, and you can figure out how you are going to draw your icosahedral face, so one triangular face. So we'll come to that, and we'll figure out, again, how do you generate different types of icosahedral faces here, right? So you can actually just create a lattice like this. Now, how do you generate an icosahedron from this? So each hexagon can be decomposed into 6 equilateral triangles, and the problem is that the hexagons are flat, right? So how do you generate this 3D structure? So if you just remove one of the triangles from the hexagon, and this is an exercise that needs to be done in 3D. So if you now just try to get this together, what you will get is a pentamer, and it will just be, it'll have a little bit of a, what should I say, a little bit of a distortion, a little bit of an edge. So you've generated a 6-fold and a 5-fold. Now, if the hexagon is actually part of a net, so the net, because you have removed one of the triangles there, so the net now has a curvature in 3 dimensions. So if you just repeat the same sort of folding 12 times, then you are actually imposing proteins on this, then you will generate a regular, eventually you will generate a regular icosahedron. So, so what you have for generating an icosahedron is basically 60 subunits. You need a minimum of 60 subunits so that you can generate the all the different triangular faces can come together, and you can generate all the 5 folds, 3 folds, and 2 folds. Now, but all viruses do not have only 60 subunits. So viruses have more than one type of protein, and all viruses are not equivalent in terms of size. There are smaller viruses, there are bigger viruses. So the question is, if you have more than 60 subunits, then how do you arrange it in the form of an icosahedron? So if you have more than 60 subunits and you want to build a bigger virus, how do you actually generate that? So the way to do it is that you have to first enlarge this basic triangular facet of the icosahedron, and then you have to subdivide it into smaller triangles. And remember those h and k values. So the triangulation is dictated by this equation. Triangulation number is equal to h squared plus hk plus k squared. And the values of h and k are either 0 or these are positive integers. So there are different ways that viruses are organized based on what are the h and k values. In some cases, h and k, h may be a positive integer, k may be 0. In some cases, h and k may be exactly equal to each other. And in some cases, h and k may not be equal to each other, but they both have specific values. So in the last case that I mentioned, and we will actually discuss this in a lot more detail tomorrow when we talk about virus structure solving by cryo-EM. In the last case, there is an issue about how to put the specific icosahedral points. So those structures can be divided into D or L. So we'll discuss that when we come to those. But basically, for most of the simple viruses, for example, for T equals 1, H is 1 and K is 0. Again, for T equals 3 viruses, H and K are both equivalent to 1. Right? So I know this does not make much sense. We'll just go forward and see. So basically, when you were talking about a T equals 1 particle, what you're talking about is that you have exactly 60 subunits, and you have arranged it in the form of an icosahedron in a very simple fashion, the way it's supposed to form an icosahedron. Now, let's say you have actually 180 subunits. How do you arrange it? So this is where the enlargement and the subdivision comes in, meaning that now in each phase, you have to have 3 molecules which are arranged, right? Now, the 3 molecules that you are arranging may not come from the same gene. So they could be the same protein, they may be the same gene product, or they may not be the same gene product. So then the idea is, how do you actually arrange everything together? So again, just to show you very quickly the different H and K numbers and how are we generating the T value and how are we generating viruses. So depending on how big of a triangular face you want, how many gene products you need to accommodate, you can have a T equals 3, particle where the values of H and K are both 1, or you can have a T equals 1 particle where the values of H is, the value of H is 1, the value of K is 0. Or you can have a T equals 4 particle. Again, there you are incorporating different values of H and K. And obviously your T equals 3 or your T equals 4 particle would be somewhat larger than your T equals 1 particle, because you are actually accommodating more gene products or more protein molecules there. And by doing this, you can have an array of different viruses. So there's T equals 1, there's T equals 3, T equals 4, T equals 7, T equals 13. I'll show you a picture of a T equals 13 virus. So you can have all of these different viruses arrayed in, with the proteins are arrayed in a particular fashion, but eventually they have to follow the principles of making an icosahedron. Now again, just to show you a little bit detail, this is a T equals 1 virus particle, this is a T equals 3 virus particle. So if you look very carefully, in this case, one triangular phase is made up of only one protein, so there's no complication. Now when you come to this sort of arrangement, which is made up of 180 subunits, so here if you look very carefully, if you just delineate one triangular component, right? So you can see that this is made up of 3 different gene products. So you have something in blue, something in red, something in green, and you are generating, again in this particle, the 5-fold, the 3-fold, the 2-fold. So the 5-fold is right there, 3-fold is right there, and the 2-fold is there. So you have generated an icosahedron with the correct symmetry elements. So just to give an example of different types of virus particles with different triangulation numbers. So you have satellite tobacco necrosis virus with triangulation number of 1. There are picornaviruses. Now this is a little bit of a misnomer here, because these are not exactly T equals 3 particles. These are what are called pseudo T equals 3 particles, and I'll come to why that is. Synvis virus T equals 4, reovirus T equals 9, herpes virus T equals 16, adenovirus, which is T equals 25. So we'll discuss the adenovirus structure when we do cryo-EMA virus structures tomorrow. Now, there was a theory of quasi-equivalence, which was proposed by 2 scientists called Casper and Klog, to define, again, some of the features of a virus capsid, right? So if you have, let's say, a T equals 3 particle, let us just take an example. If you have a T equals 3 particle, so each triangle here has 3 subunits, and if you had only one protein, let's say just a very simple test case, you have a T equals 3 virus, but you have only one protein, then how are you arranging it in terms of this icosahedron? So this is where the theory of quasi-equivalence comes in, that you have these subunits which are more or less equivalent because they are coming from the same gene product, they're the same gene product, they're the same protein, but the way that they have been organized is not the same. So if this makes any sense, you have the same protein. So if you have blue and red and green, you have the same protein here. However, their surroundings are not the same. The way they're interacting with their neighbors is not the same. So this is quasi-equivalent. So equivalent molecules, but behaving in a quasi-equivalent fashion. So why does this become important at all? So as we will see tomorrow, actually, what happens is that different parts of the proteins that go into making up this quasi-equivalent structure, they may be doing different jobs based on where they're located and what is their interaction with their neighbors. So the quasi-equivalence theory actually explains quite a lot about the different functionalities of different parts of the virus structure. And again, you can see the generation of the pentamers and the hexamers. And even if the protein is the same, it has been arrayed in a different way, and different parts or the same part of the same protein, depending on where it is located in the virus structure, can carry out different functions. So, just to show you, this is what I was talking about. This is the Virus Particle Explorer website, or ViperDB. And if you have any interest in playing with icosahedrons or figuring out how to make different viruses with different triangulation numbers, you can go here. You can pick whichever one you want to do. It may be fun. A lot of people do it, is that you print out this hexagonal sheet and then you cut it out, and then you cut out one triangle and you try to see physically if you can make an icosahedron. So, right. So just to show you again a structure of blue tongue virus, which has a triangulation number, I think, of 13. And the adenovirus structure has a triangulation number of 25 that we'll discuss in detail tomorrow. So it's very complicated, but the reason that viruses were utilized very extensively initially for cryo-electron microscopy studies is because of the extensive amount of symmetry that is present in these molecules. So this slide I just borrowed from Vinod after he stopped talking. So this is Crowther's paper, again from 1971. And you can see that the way that in the projections of the calculated projections of different orientations of the virus, you can very nicely see the different symmetry axes that are present. And one of the reasons why I think viruses were used initially is also because of the ease of sample handling. So we have been talking quite a bit about smaller molecules and what to do in order to get the signal from the smaller molecules, and how to optimize the signal to noise ratio when you're working with smaller molecules. But the good thing about viruses is that it's not usually a bit of a problem unless your microscope has significant issues to get decent images. The ice doesn't have to be very, very thin. Usually, if you don't have a thin carbon layer on top of your grid, you can still get away with it. You can still get nice images, and eventually you have each projection corresponding to, so 60 different projections should be similar in the sense that you have 60-fold views of the icosahedron. So, so we'll talk in detail about virus structures and the biology of virus structures, which again I think is more important, and what we learn from there, and whether if we solve a structure we can actually answer biological questions or not, or based on quasi-equivalence, actually how does the structure change, how does the functionality change, and can we again address questions related to it. So we'll come to those things tomorrow. So, so just to summarize, some examples of different point groups from PDB and EMDB. So you have CNs, DNs, tetrahedral, octahedral, icosahedral, and then the extension. So you have N is infinity, so helical structures. So in the point group chart now, how do you actually identify what you have? So if you see only cyclic CN, so if you just see one rotational axis of any kind and maybe anything, then the symmetries are CN. if you see a Cn, again n may be anything, and plus you see a C2, then you may be dealing with a dihedral symmetry. If you see C3n, C2, this may be a case of tetrahedral symmetry. If you see C4, C3, C2, then you are seeing an octahedral, perhaps an octahedral molecule. And this is really a signature of icosahedral molecules. If you see a C5, which is that 5-fold axis of symmetry that I was showing you, if you see the 5-3-2 symmetry, 5-fold, 3-fold, 2-fold, then this is probably a case of icosahedral symmetry, which would make your life very much easier as an electron microscopist to get, you do not have to get a lot of particles in order to get a decent reconstruction. So I will end here, and if there are any questions.
Thank you, Manideep. A very nice summary of symmetry in 2D projections. I have a specific question regarding how you quantitate the symmetries in EM projections, because in crystallography you have a nice method of locked rotation function or self-rotation function.
Right.
To figure out
you
the
can
NCS.
do.
So is there a method or a tool to do that?
Yeah. So in crystallography, you particularly to give an example for icosahedral viruses, you are looking for that 5-3-2 locked rotation function, and you get a nice peak, and from there you can say that this is where the molecule is and what is the symmetry. So for quantifying symmetry, I think I showed one slide. Let me just go back.
There's a one-dimensional correlation plot.
Right. Looking for it. Right. So this molecule here has 6-fold symmetry, and it is possible to do sort of a correlation of the molecules. So you take a rotational power spectrum, and you are just looking at the basically the harmonics based on symmetry, rotational symmetry. And since this is a 6-fold, you can see that at these different rotational harmonics at 6 or at 12 or at 18 or at 24, you are seeing a nice peak. So, but then again, when you are having something that is dihedral, again, you have to go back to the projections and try to make sense of the projections, because cyclic and dihedral, there's chances of...
most cases, I guess, you
right.
already know.
Right. So that's a very good point. So in most cases, you know what you're working with. So if you're working with a ribosome, you know that there is no symmetry. If you're working with any sort of mutation of GROEL or GROEL bound to something or the other, unless it does something drastic, you know what kind of symmetry you're going to get. If you're working on icosahedrons, then again, you know what sort of symmetry you're going to get. The problem comes when you are dealing with something that you really don't know what it should look like. But again, as Vinod was pointing out, when you're doing biochemical studies, you have some idea of what is your molecule, right? So whether it's a dimer, it's appearing as a dimer or a tetramer or whatever. But to extend that a little bit, so one of the things that we do for icosahedral reconstructions actually is, so you can impose whatever kind of symmetry you want, right? So you can impose the symmetry group, point group I, or you can impose other point groups. So we always try to do one reconstruction with C1, just to see if we are getting that 5-fold, which then indicates that the data is probably good.
In general, since it was several times mentioned about the statistical analysis, you can apply statistical analysis with a certain type of use. You can select those images which belong, for example, to the classes which you are trying to determine the symmetry. But in this case, I would recommend to use, for example, that's what you call as end views. And to do statistics, you have to center the image. It's essential to do centering of the image. And then you can go into, I would say, any principal component analysis, MSA analysis, magic spider, possibly it's would be possible in Reline, and definitely you can do that in XMIP. And in this case, you have just to analyze and to look at the eigenvectors, which would be, for example, very often the third or the second, sometimes fifth or second eigenvectors. And suddenly you can see very, really nice flowers. And in general, you have used the images on the latter toxin.
Right.
For some reason, you've used only one image, but you didn't show the images of eigenvectors from the same paper.
Right.
It would be useful if you will look at that. And it's just since the biochemistry was indicated, latter toxin is a dimer. But when we look at the images, it was actually even the sizes of the images and the images, they didn't correspond to any dimer. It has been turned out that it was a tetramer, cyclical symmetry C4. So we have just did statistical analysis, and it was absolutely clear. It's a strong four-fold symmetry, and
Right.
it has been just shown. We didn't assess, we didn't check, but we just did statistical analysis.
Thank you for the nice introduction for the symmetry. And I have one question about, since for basic point of view, I realized you didn't classify it as inversion center groups. You classified group with rotation symmetries and with some of them with mirror symmetries. I will also introduce the combination of rotation and mirror and generate inversion center directly.
Right.
Well, however, for crystallography point of view, some signs, I mean, not always, I'm just curious. So when you do Fourier transformation from the phase part, if you have an inversion center, and the phase could be sometimes limited to 180 and 0. If you put the original of the phase to the inversion center. I don't know if it's clear or not. So in the old times,
I'm not quite. So you're talking about a rotation and then a translation?
No, not translation.
In terms of a crystal or no?
Not translation.
Okay.
I mean the inversion center. If you have an image with the inversion center or 3D object with the inversion center, if you do Fourier transformation of this two-dimensional or three-dimensional object, you get a Fourier map or Fourier 3D map. In this case, in the phase part, it should be like 180 or 0.
Yeah, but in biological
Yeah, but
systems,
we use it
Getting
here when we have like a D2 or some symmetry has inversion centers. In the, I mean, for the calculation of final maps. Since I don't know, so
oh, that's only possible for non-chiral molecules, right? In biological systems, we don't deal with those space groups or symmetries with inversion center.
But we also have objects with the inversion center, right? But like molecules with. In D2, D4, I think, right?
Will it have inversion center? It will not have inversion.
D2 we do not?
It has.
No, it has just. Yeah. It cannot have actually. No, it's not.
So if you have a two-fold symmetry and
when you just this one and this one, that is
yeah, that won't work.
Yeah.
So which means we do not have inverse center in this.
Yeah. So maybe you can.
So dihedral is two cyclic symmetry
Inversion.
axes.
Two plus inversion,
So,
plus mirror, yeah.
So, yeah, what you're talking about is in crystallography, it's centric reflections. So centric
Yeah, yeah.
reflections will have 0 and pi angle.
Yeah, yeah, yeah.
And in proteins, you will not have a right-hand helix and left-hand helix. So
So
that is not
I-
possible in proteins.
I don't know if
Basic
you're
have
concept.
inversion
Yeah.
center. So it's always a right-hand helix.
Oh.
so if you're
Yeah.
talking
So
about
Central
as-
section. Central section.
As I keep telling my students, always there is exception for biology. Always, whatever you talk, right-hand helix.
Yeah.
There are exceptions in exceptional cases, but most of the time in humans, the proteins are always
Oh,
helices
wow.
are right-handed, so you cannot have an inversion center.
so
that's why
if
it's
you're
not
talking
dealt
about
in detail.
reciprocal space,
Yeah. Oh,
But-
no, I think Natish already, and Professor
Okay.
already answered my question. I think I get the point. That's a basic concept
Good.
of biologists. Now I
Good.
understood.
Excellent.
Thank you for that answer.
Excellent. Yeah. Any more questions? Symmetry is always beautiful whenever you see. That's why crystals always look beautiful, isn't it? So, thank you very much for a very nice and beautiful talk.
and viruses
And
are also very beautiful, and
viruses.
we'll do that tomorrow.
Thank you very much, Manideepa. We'll go for lunch, and then, as usual, we'll gather at the reception at 1:15 so that you can catch the bus. Thank you.